Good afternoon. My name is Oleg Poznyakov, a PhD student at the National University Zaporizhzhia Polytechnic. My talk is about a multi-agent architecture for legacy custom code migration to SAP S/4HANA. The slide shows the structure of the talk. We have 8 parts, from the problem and existing tools through the formalization and system design, to the experimental results and conclusion. Enterprises worldwide are migrating from SAP ERP to SAP S/4HANA. A typical installation contains between 2 and 10 million lines of custom ABAP code, years of accumulated business logic specific to each organization. Static analysis tools can spot deprecated constructs but cannot migrate the code. Manual migration requires thousands of person-hours of skilled ABAP developers. The key inside migration is fundamentally different from code generation. In generation, the model is free to choose any solution. In migration, the source code already exists, and its business logic must be preserved exactly, requiring a formal equivalence metric. Migration also requires deep SAP domain knowledge that standard language models lack, and SAP licensing forbids sending custom code to cloud services, ruling out most modern AI tools. The slide compares existing frameworks across 6 criteria: MetaGPT, ChatDev, and AutoGen, a build for generating new software from a description. They have no concept of source code to preserve, no equivalence metric, no SAP domain knowledge. Cloud Code and Google Antigravity are the latest commercial tools, but they run via cloud APIs, violating SAP licensing. None of the existing system satisfies all key migration requirements at once. The goal of this study is to improve the quality of automated legacy custom code migration through multi-agent LLM architecture. 3 objectives: formalize migration as a Markov decision process with an equivalence-aware reward, develop a planner developer reviewer architecture, and measure each component's contribution on 300 real ABAP fragments. The on-premise constraints is not just a policy requirement, it directly shaped the model selection. The system runs on a single NVIDIA A140 GB GPU using open-weight Qwen 2.5 models, which can be deployed locally without any cloud dependency. The migration process is formalized as a Markov decision process. The state at each step is the migrated code described by 3 quality metrics: syntactic correctness measured by the above-linked static analyzer, function correctness measured at S1 on unit tests that cover the business scenarios of the source code, and semantic similarity to the original computed via CodeBird embedding. These 3 metrics are combined into the EAQS, the Integral ABAP Quality Score. The key distinction from code generation is the reward function. It implicitly penalized any deviation from functional equivalence with the source, not just rewards work code. In this work, EIQS is used for the first time at an online stopping criterion built into the agent loop, not as a post hoc evaluation tool. The reviewer agent accepts the result only when IAQS reaches the threshold of 0.76 established empirically in prior works. The system has three agents. The planner analyzes the source code and builds a migration plan using RIG over 12,000 SAP nodes, official documents describing deprecated constructs and replacements, and the simplification list cataloging changes in SAP S/4HANA. The developer agent implements the plan and from the second iteration applies target fix based on reviewer feedback. The reviewer agent runs two-stage validation, automatic IAQS computation, and if the threshold is not reached, structured feedback with classified issues. The planner review agents use Queen instruct model. The developer agent uses a fine-tuned Qwen coder model. All three run separately on a single NVIDIA A140 GB GPU. This is what makes the system deployable in enterprise environments without sending any data outside. The diagram shows the iterative protocol. Step 1. The planner produced a migration plan. Step 2. The developer generates code and from iteration 2 applies feedback. Step 3. The reviewer computes IAQS metrics, receiving both generated and original source code, enabling functional equivalence verification, not just compilation check. Step 4. If IAQS metric reaches the threshold, result is accepted. Otherwise, the cycle repeats up to 3 iterations. 97% of fragments resolve within this limit. The dataset: 300 real ABAP fragments from a live SAP ERP 6 to SAP S/4HANA migration project, split by complexity: 102 low, 126 medium, 72 high. All experiments run on a single NVIDIA A140 GB GPU using the vLLM inference engine. For configurations compared zero-shot single model baseline, same model with chain of two agent system without a planner, and the full multi-agent system. Each run 3 times with different seeds. Statistical significance confirmed by peer t-test. The chart shows clear step-by-step improvement with each architectural additional. The planner agent contributes most. It brings domain knowledge the other configuration lack. Overall, IAQS metric improved over 17% gain of a single pass generation. Syntactic errors dropped 3.7-fold, and all results statistically significant. Tables present detailed result across of 4 metrics and complexity levels. Every architectural addition improves all metrics together: syntactic, functional, and semantic. The complexity breakdown confirms that the multi-agent advantage grows with task difficulty. The gap is largest where the task is hardest. The multi-agent system gain over zero-shot roughly doubles as complexity increases from low to medium to high. The gap between the two-agent baseline and the full multi-agent system grows in the same way, showing that the planner's contribution scales with task difficulty. The more duplicate constructs involved, the more critical SAP domain knowledge becomes. The scientific novelty of the work lies in the further development of the multi-agent architecture for legacy custom code migration through the formalization of the migration task as a Markov decision process with a reward function based on the IAQS metric. In contrast to existing approaches, this provides a formalized online stopping criterion for the iterative interaction cycle between software agents, the planner, developer, and reviewer. Furthermore, the IAQS metric itself is extended from a post hoc evaluation measure to an integral component of the decision-making process within the iterative multi-agent loop. Practical result: over 17% improvement in the integral quality metric compared to single pass generation, fully on-premise deployment, SAP licensing compliant. Further work: learnable policy based on reinforcement learning from human feedback, dynamic agent orchestration, scaling to the other ERP platforms. Thank you.